Hi everyone, my name is Joe Bringley, and I did my project on facial recognition using principal component analysis. Just one note before we begin. This is an implementation project. I meant to do it in Python, but I encountered a lot of difficulty just even installing the library required. So this is in MATLAB actually, contrary to what my project proposal says. So let's begin. Here's my outline. I'll give you my problem statement and motivation, show you what others have done to try and solve this problem. I'll go over a very brief explanation of what PCA is. In the eigenface method, I wasn't able to get in contact with Michael, so if he wants to go into more detail, that is fine. I think that might be best. I'll show you the data that I worked with, my approach, and then the results that I got. So, my problem statement. So, I wanted to create a facial recognition system using this eigenface method that accepts as user input an image, and I have a database already there. So it accepts an image and it compares this input image to the images in the database, and it tries to identify the input image and match it with an image in the database. And the next bullet point kind of leads into my motivation, which is not just to implement this project, but to understand this eigenface method and PCA and see why it works, why it fails, what are the conditions where it works and fails. And that's kind of the question that I'll be addressing throughout this presentation. And so the next slide is my attempt to explain PCA. Please excuse the artwork, and obviously I only have 10 minutes, so I don't have enough time to go through this, but I'll try to explain the best I can in just a few short sentences what PCA does, or specifically what the eigenface method does in an attempt to recognizing the face. So if you see here, if you have this training set consisting of P images, what you do basically, and there are a bunch of steps here, but basically what it boils down to is you want to represent each image in the training set by a linear combination of these things called eigenfaces. These steps here show you how to compute these eigenfaces. But what basically you have is, so you have each image in the training set, and it corresponds to a certain percent of each eigenface, right? And these percents, or these weights, you can form a weight vector. So each face in the training set gets assigned a weight vector, right? And so how does it recognize a new face, right? How does it match faces? So when you get a new input image, what it does is it does all these calculations here, but it computes the input image weight vector. And then, using something called this distance metric called the Euclidean distance, which I think basically, to explain it, just computes the similarity between two vectors, right? So it goes through each one of the weight vectors in the training database, and it tries to see which one is most like the weight vector for the input image. And the one that has the minimal distance to that input image is the one which it will say, we think this is a match. So that's kind of, my brief explanation. And let me tell you a little bit more about PCA and related work. So PCA for facial recognition is actually one of the least efficient algorithms. And you'll see why in a second. It's easy to understand, not very hard to implement, but it's not always that efficient. And one of these reasons why is one of these steps here is that you have to compute the average face vector, right? So you take up all these vectors in the training data set, which represent an image, and you compute the average face. But that can bring a lot of problems if you have different lighting, different poses, and you'll see that in a second. So people have tried to improve on that. So what have they tried to do to improve? One of the things is spatial transforms. So the idea of center normalizing head orientation has actually, it was a more recent paper, but even that paper with that method came up with unsatisfactory results. So there have been more simple techniques applied, and it mainly doesn't apply to the algorithm itself, but to the images before the algorithm sees them. These pre-filtering techniques, ideas of to eliminate the effect of lighting, this idea of a color classifier, which removes pixels which have a different color than the average skin. And so here I'll quickly show you the data that I was working with. So this is a data set which I found online, free data set. And as you'll see, the depth of each image is very similar, the lighting is similar, the head orientation is similar. And when I ran the eigenface method with this, it was 10 out of 10, correctly identified each of the 10 persons involved. Not very, nothing really that interesting. But what happens when you get a slightly less controlled data set? So what I did is I asked 12 of my friends to send me 3 pictures of themselves. So to send me 2 for the training data set and 1 for the test. And so I'll show you a snippet of that. And so you'll see this is slightly less controlled. The orientation is different. He's wearing a hat here. The angle is different. The lighting's different. Even this person, one is very up close, one's kind of far away, and then this is just a snippet, by the way. There is more. And then here I'll come back to this data set. But so my approach was to apply the eigenface method, which is some of my code here, but expect that some of the results might be unsatisfactory. So then think of the background as noise and try to eliminate the effect that the different backgrounds have on the images, since I don't have a controlled background in these. And so to reduce this noise, I applied just some Gaussian smoothing and MATLAB to each of the images in the test and the train databases, excuse me, and see where that got me. So result-wise, and this is for the original data set as well as the one with Gaussian filtering, they both had the same results. 8 out of the 12 people were correctly identified. And as you'll see here, there were some not pretty results. My friend Kate was not happy to be identified as a man. But why did I get these results, right? What's interesting about these is, so in terms of my interpretation, so if you look here, I have 2 from the controlled data set, right, where the lighting is the same, the background's the same, and here's the average face of these 2, right, which is a pretty good estimate of the average face. But if you take these 2 images in the data set, here is the average face here, right? That is a very bad estimate of the average face. And so the reason why for these results, at least in my conclusion, is because the eigenface method examines the whole face, the entire image, I'm sorry. It doesn't examine just the face, but examines the entire image here. So it's when you're computing this average face, which comes into play a lot with the calculations, it's not really the average face, it's the average image. And so you'll see all this stuff around his face and all this stuff around her face. It gets filtered into a result which shouldn't, right? This is the average face between those 2. And obviously, as you take, the sum of more faces and divide them, it will get more normalized, but still you're going to have a ton of kind of obscurity because it doesn't look at the face, it looks at the whole image. So the thing which it calculates as this is the average face is not the true average face. So that is why I think was the reason to it fail, is because when you're examining the entire image, this calculation of the average face is not a true average face. It's the average image. So you're subtracting the average image off of these image vectors, and you're not getting accurate representations of the people's faces. And then finally, so for future work, in the following week, I would like to do some more pre-processing techniques. I didn't get any improvement with Gaussian filtering, but I was reading a paper actually right after I finished up this presentation of transforming the images into the HSV color space with the idea that that could reduce the effect of illumination and lighting on them. So that would be something which I would look forward to kind of experimenting with in the next week to come. And then as for where else can this apply, I think handwriting analysis would be pretty cool place to apply the eigenface method. I think it'd be easier to zero in on a single letter than kind of a whole face in an image. And if you can zero in on a single letter, being able to compare handwriting styles and try and match the style to a person. But yeah, that's it for me. I think I went over my time. There's my references. Thank you.